Problem 1 on set 13 involves a supercritical flow suddenly becoming subcritical through the process of a hydraulic jump. This is a diagram of a side view of the situation represented in Problem 1, while this is a view of the cross-sectional area. We will be using the given values from the sheet, not the ones that we found in lab, because each section has different values. We calculated the cross-sectional area of the supercritical flow and the speed, because these will be important in later calculations. Problem 1a asks us to prove that the flow is supercritical on its approach. The flow is supercritical if the Froude number is above 1. This is an easy way to tell. The formula for the Froude number is velocity divided by the square root of gravity times the depth. In this situation, the Froude number equals 3.39, which is greater than 1, so the flow is supercritical on its approach. Question 1b asks us to classify the hydraulic jump using the Froude number. Since the Froude number is 3.39, it falls between the range of 2.5 and 4.5, which indicates that this jump is an oscillating flow.
Part C of question 1 asks to find the depth of y2. We can use this by using this equation found in the book, but note this equation can only be used for rectangular channels, and since we have a rectangular channel, we can use this. Plugging in the values of y1 as 0.083 feet and the Froude number of 3.39, we can easily find that the y2 depth is 0.358 feet. Part D of question 1 asks to find the head loss through the jump. We can find the head loss using this long equation. Now note that it's y2 over y1 here, and then it switches to y1 over y2. Plugging in the value of y1 equals 0.083 feet, y2 of 0.358 feet, the Froude number of 3.39, we can get a head loss of 0.173 feet, or that is 0.0527 meters.
For question 1e, you have to find the critical depth, and then you have to plot the whole entire specific energy equation. We start off by trying to find the critical depth. In order to find the critical depth, we must find the flow per unit width. In order to find that, you take the Q, which is the flow rate, over B, which is the width of the channel. Plugging those numbers in, you still get the 0.46 feet squared per second flow. Then, in order to find Y critical, you use this equation, Q squared over G. Plugging in the values of the 0.46, which we got up here, and gravity, which is 32.2 feet per second squared, since we're in feet, and that's all the power of 1/3. Using this calculation, you achieve an answer of 0.187 feet. In order to find the specific energy, we use this equation right here, which is the depth plus the flow per width squared over the 2 times gravity times the depth squared. For example, we found the specific energy for the critical depth, and that answer is right here, 0.281 feet. Using the equation that we found earlier, we take the y and add 0.01 feet to each interval. Then we find the corresponding specific energy using that equation shown there. When you plug all the points in and find the graph, this is what it should look like. Then you find your y1, which is 0.083 feet, your yc, which is 0.187 feet, and your y2, which is 0.358 feet. Then, to find your head loss, you go right here to find the length between the y2 and the y1, which in this case would be 0.173 feet.